So we'll be talking about equations of lines and planes. Um, this topic has a lot of visual intuition involved, I guess. So we'll see how this goes. So a line. Say that we have 2 points in space. Call them P and Q. What we can do in order to describe a line from between P and Q, or a line that passes through P and Q, what we'll need is what we call the direction vector from P to Q. So um, our convention is going to be to label this with to have the values of the vector be labeled A, B, and C. Now you can clearly see that in order to create this direction vector, all you need to do is Q minus P. You just would calculate this vector, right? Which involves subtracting the components for Q or I might be saying it backwards. The components for Q minus the components for P will give you the direction vector. Okay. From that, you can piece together this first form for a line, which is called the vector equation of a line. So the way that you can intuit how this formula works is if t is equal to 0, then we have the point x naught, y naught, z naught. So we're forcing this point, P, to lie on the line. And then the next part is, well, the direction of travel. Imagine that t is now 1. You've taken a time step forward. And so the whole vector is supposed to then travel by, well, the direction that the line extends in, which is ABC, the vector ABC. And so this captures, this traces out a line if you extend t from minus infinity to infinity. Okay, this is a way to describe a line in vector form. Now, to get to this next form, the parametric form, what you do is isolate the components of the vector form. So you can combine all of this together into a single vector and then take the x component, y component, and z component, or you can kind of just read it off, right? So for example, the x component, you'd get x is equal to x naught plus t times a, which is this first equation. And then you can do that for the other two. So that's the parametric form. The last form is the symmetric form. So in order to get to that, what you do is you take the parametric form and then you solve each of the equations for t. So we end up subtracting the x naught and then dividing by a, for instance, and that this is equal to t. And then you do that with the others, and you get this form of a line. Okay, and that is what I've remarked below. Before we talk about an example of this, let's just extend this idea to a line segment instead of a full line. So a line segment, what we do is we're bounding a line. Instead of extending infinitely in both directions, we go only from P to Q and no further. Okay, there are two ways of depicting this. So one of them, this expression, you'll get used to the way that this works. So notice that in this expression, if you plug in t is equal to 0, this second term becomes 0, and you are just left with p. So that means that this vector equation contains the point p, or contains well, it points to the vector whose associated coordinate is p. I'm beginning to conflate points and vectors, and which is a very standard thing to do. Although it's I try to discourage that and I try to be precise, but it's useful to be able to note that to any point in space, we're associating the vector whose initial point starts at the origin and whose terminal point is the coordinate that we're talking about. Yeah, so going from the capital P and Q to the boldface lowercase p and q is just There's an association between the two. Okay, so yeah, at what were we saying? At t equals 0, we have the point P, and at t equals 1, we end up with the point Q. So, and this is a linear equation. So, this means that this traces out a line that passes through the points P and Q. And if we enforce the time t needs to lie between 0 and 1, then it only goes from P to Q, and it does not extend further beyond it. And so this is an equation for the line segment extending from P to Q. And from that, we can get the parametric equations of a line segment. So the idea is the same as before. You end up solving for the components. Now, I didn't bother to write out what P and Q are explicitly. You would end up doing the calculation. I guess I can do it off to the side since maybe some of you can't see what it would be. So R would be the X, Y, and Z. It's free-ranging kind of information, a point. You have 1 minus t. P is that, X naught, Y naught, Z naught. Plus, and then t multiplied by x1, y1, and z1. And then is it possible to solve it from here mentally? Kind of, yes. So if we just focus in on the x coordinate, let's say, we would get 1 minus t times x naught plus t times x1. And then collecting, you get plus t x1 minus x naught. Right, I end up factoring, I distribute the x naught and then I factor the t out, and I get the following. And that works for all three coordinates. You should also notice that there's some similarity between the parametric form for the line segment and for the equation of a line. We just have to be a bit more careful about the fact that this extends. So this ends up replacing the A, B, and C that are part of the direction vector. But if you actually think about it, this is how you would have computed A, B, and C. A, B, and C you would have gotten by doing Q minus P, which is exactly this quantity. Q minus P, yeah, in that order. Okay, so yeah, there we have it. The parametric equation for a line segment. Now for example. So we're asked to create all sorts of equations that describe the line passing through the point P and Q given. So the vector form, well, we start at a point, so we have the point here. And to create the direction vector, we just subtract Q from P. So I don't know, maybe I can write that out. So this would be, I'm thinking of 4 minus 7 comma 2, subtract off negative 3, 5, 9, and that ends up being the direction vector V, which is 7 minus 12, negative 7. Just double checking that looks right. Yeah, that looks right. So there we have it. Next, for the parametric equations, the procedure is to isolate each of the component functions. So x ends up being minus 3 plus 7t, y is equal to 5 minus 12t, and z is equal to 9 minus 7t. And so we get that. For symmetric form, we solve for t. So yeah, as you can see, it's just add the 3 over, divide by 7, minus the 5 over, divide by negative 12, minus the 9 over, divide by negative 7, and that solves for t. And then for the last part, we want the parametric equation of the line segment determined by P and Q. So just the line segment, not the full line. Notice that all we actually end up doing is fixing t. Well, we restrict the values of t. So initially t could be all real numbers. We restrict that down to just the interval 0 to 1. And yeah, the parametric equations themselves are the same. You see, which is the comment that I made earlier that these quantities x naught minus or x1 minus x0, y1 minus y0, z1 minus z0, these are actually a, b, and c that form the direction vector. Okay. Now here's a common problem to do. Given a line and a point not on that line, can you determine the distance between the point and the line? So we have the following formula. So given the line L with direction vector v and m, a point not on the line, the distance, which in this picture is this dotted line, and I'm denoting its length by d, this distance can be computed by this formula. We need to take the magnitude of the cross product divided by the magnitude of v. Okay, and P can be any point on the line. So basically you can just pick a point on the line that's convenient for, either convenient to see it lies on the line or maybe convenient to do the computation in. The book doesn't cover this very well, so I've like sort of reworked the way to present this information. So, okay, the proof. Let's talk about why this formula makes sense. So it boils down to considering the area of this parallelogram in red and just writing the formula for the area of this parallelogram in two different ways. One way involves the cross product, right? This parallelogram is spanned by the vector v and the vector from P to M. And so it's the area is the magnitude of the cross product of these two vectors. That's the first way we can write it, which is here. And the second way is we think of base times height for a parallelogram. Base, we can let that be the side given by the vector v, and the height is going to be this distance vector. So the distance is the length of the line that is perpendicular to the line L. You can see that I'm denoting it that way because that minimizes the distance. You can have all kinds of lines, but the only the distance is going to be the one that has minimal length, right? And so yeah, this ends up being the height of this parallelogram, and so it's going to be the length of this side, which is the magnitude of v times the height, which is d. And then by solving for d, obviously, you end up with this formula. So that's why we know this formula. Okay, using this formula, so say we have some point A and a line of symmetric equations. So your problem also deals with symmetric equations. You could describe the line in, well, one of three different ways, as in what we talked about previously, using a vector form, the parametric form, or symmetric form. Either way, we have to use this formula for distance between point and line. So this is how we proceed. I first try to determine a point that lies on this line. Very clearly, you can see that the point 0, 0, 0 is on the line, right? I plug it in, and yes, we do get 0 equals 0 equals 0. So yeah, that point is on the line. Great. Also, in order to do this computation, I need the vector v. I need to know the direction that this line extends in. So looking back at the symmetric form, we want the symmetric equations to be of this form, where we have the components of the direction vector are in the denominator, the a, b, and c. And then we have these like offsets, but they don't show up in this problem. So, okay, let's see. Now, the way that the symmetric equations are set up here, we don't have anything in the denominator, but we also have these numbers in the numerator, which we don't want, right? They weren't there in the symmetric form. So what we have to do is actually divide. So we divide by 2, and this negative I can just put into the denominator for this formula, for this function. So we would get x over 2 is equal to y is equal to z over negative 2. now that I've divided by 2, this does fit the form of a symmetric description for a line. And so then you can read off, especially if I put a divide by 1 there, you can read off the A, B, and C that forms the direction vector for this line, which is V here. And finally, I'm just stating one check that we should do just to make sure that things are consistent, or to make sure that the problem is set up correctly, which is that the point A should not lie on this line. Well, when we plug A in, then we get 2 equals 2 equals 3, which is clearly not true. So because of this -3 in this coordinate, this point is off of the line, which is good because that means we can compute the distance. I mean, if the point was on the line, then the distance would be 0, clearly. Since it's off the line, we use the formula. So we go ahead and compute that. M in the formula is the point A that is off the line. So, and the point P is 0, 0, 0. So we construct the vector from P to A, doing A minus P, which gives you the vector 2, 1, minus 3. Easy to compute. And then the vector V is 2, 1, minus 2. We take the cross product. Okay, before that, the magnitude of V, that's pretty easy to see, right? It's 2 squared plus 1 squared plus -2 squared, so 4 plus 1 plus 4, which is 9, in a square root gives you 3. This cross product, I didn't bother to write it out. Perhaps I can do so since I'm doing this recording. So ijk 2, 1, minus 3, 2, 1, minus 2. So we end up getting, for the first part, so I'm cofactor expanding on the top row. For the cofactor corresponding to I, we would have these 4. So it's -2 minus -3. So we end up doing +3. And for J, we have a negative in front because of the sign alternation. The main diagonal gives you -4 minus -6, so +6. And lastly, for K, we get 0 because it's 2 minus 2. And simplifying that, we do end up with 1 comma -2 comma 0, which is that. And then the magnitude of this, 1 plus 4 is 5. Take the radical, you get √5 on top. So there we have it. That's the direction, distance. Right. Now, descriptions of a plane. So, the main thing to capture about the plane is its orientation in space, which can be determined by something called the normal vector. So the normal vector is this vector which is actually perpendicular to any line or any and I mean, in this case it looks like a ray, but it's perpendicular to any vector that is on the plane. Right? So we call that normal instead of words like perpendicular or orthogonal, but normal means the same thing in this context. Okay, so now set P to be a specific point that lies on the plane. And Q, think of it as a variable, or as a coordinate that we're allowed to range freely, as long as it's on the plane itself. So Q we would think of as just being X, Y, and Z, subject to the constraint that it also must lie on the plane. Okay, so then we can create what's called the vector form for a plane, which is that the normal vector dot producted with this vector from P to Q equals 0, which should make sense if we think about the geometry here. So the normal vector is supposed to be perpendicular, orthogonal, and one property that we know is that the dot product detects orthogonality. If the dot product of two vectors is equal to 0, you know that they are orthogonal. And so this equation is actually describing, basically it's specifying the Q is the set of all points such that the vector PQ is orthogonal to n, and this ends up sweeping over the entire plane. This is a nice geometric way of describing, yeah, the property that the uh, the plane described by the normal vector n is the set of all lines that are orthogonal to n. Okay. Continuing. So from the vector equation, if we insert this a, b, and c in here, and we do the computation q minus p, and we get another vector there, and then we take the dot product, we end up with the scalar equation of the plane. So just to write it down, a, b, and c, if we dot product it with q minus p, it's x minus x naught, y minus y naught, and z minus z naught equals 0. Right? I'm just substituting into the vector equation, and I get this form. And then doing the dot product, we end up with the scalar equation. Okay, so this is another nice way to describe a plane. And lastly, you have this one, which can show up. It's a little bit less nice because in this scalar equation, you can easily read off a point that lies on the plane, the x naught, y naught, z naught, and the direction, or the normal vector, a, b, and c. So this is a rather useful form for the equation of a plane. This is a bit less useful, but it's still worth discussing. So all you do is you just expand it out, distribute out the a, b, and c, and collect things over. So d is just set up to be minus a x naught minus b y naught minus c z naught, as shown here. And that is what I remark. Okay. Now for an example. So suppose you have a point P and a normal vector n, and you want to describe the plane that possesses that normal vector and that passes through that point P. So, well, we want the scalar equation and the general form. The scalar equation, well, you just literally plug the values into the scalar equation. So a, b, and c are 4, 5, and 6 respectively. X naught, y naught, z naught are 1, 2, and 3 respectively. And so that gives you this equation. And then for the general form, we just distribute, and you get that. I think this is the last topic. Let me try to remind myself. Yeah, this is the last page. So distance between a plane and a point. So consider this diagram. We have this plane, and we have the point P that is off of the plane. So in order to calculate the distance between the point and the plane, we really want to be thinking about the length of this line. So we might be able to easily come up with a point Q that lies in the plane, and to then be able to construct this vector QP. But then the actual vector we want the length of is this vector RP, and we don't know what R is. But what we can do is we can take QP and project it onto the normal vector N, because that is going to have the correct direction. You'll end up with the vector RP by doing the projection. And then from taking that projection, you want just the length. So that is where we start. From the vector QP, we project it onto the normal vector, and we only take the length, the magnitude. That is the same as saying we want the scalar component of the projection, which the book uses this notation, and we have absolute values because it could be that the direction that this could be a negative number, but we want it to be positive because we want it to measure the distance. So we just take absolute values. And then if you look at the definition of what the scalar component is, it's this vector dotted with this vector divided by the magnitude of the vector you're projecting onto, which is this expression here. And again, the absolute values are just because the dot product could be negative, but we want the distance to be positive. Okay. And in the case where you have all these specific values, so this theorem is particularly just if you have the point P with the coordinates x0, y0, z0, and your plane is in the general form of a plane, ax plus by plus cz equals k. The book uses a k instead of d for whatever reason. Oh, well, because d we want to be distance, so that's why we switched the variable. That makes sense. So it's given by this formula, which is the result of just plugging things into here. So I end up proving it below. So the normal vector n is, we can read it off of the general form. It's going to be ABC. And suppose that Q is some other point, x1, y1, z1, that lies on the plane. Well, the vector QP is then going to be this vector, and n is ABC. The magnitude of n is the square root of a squared plus b squared plus c squared. Taking the dot product gives you this. And lastly, so this is this one step maybe we need to think about for a second. You distribute things out, and so you can definitely see the first three terms coming from the x0, y0, and z0. But the x1, y1, and z1 seem to disappear. Now this is because we force that the point x1, y1, z1 lies on the plane. What that means is when I plug this point into this equation of a plane, right? What that forces is it forces that ax1 plus by1 plus cz1 plus k is equal to 0. And notice that when we do this distribution, we have minus ax1 minus by1 minus cz1, which basically means that we've moved these three terms to the right-hand side, which means that it equals k. That's why k shows up, and that's how we get the formula that is described in this theorem. Okay, and so the corresponding example is to just use the formula. You are given some point, and you're given the equation of a plane in general form, then you literally plug the values in. So we have the direction vector ABC comes from the coefficients in front of x, y, z, so it's 4, 5, 6. K is 7, and the x0, y0, z0 are 1, 2, 3. And so computing, we end up with 3 over radical 77. And that's all I've got for this topic.